Welcome to Academic Engineering. Today, we're diving deep into one of the most fundamental concepts in heat transfer and fluid mechanics, convection. But we're not just scratching the surface. We're going from absolute basics to professional-level understanding of dimensionless numbers that engineers use every single day. By the end of this lecture, you'll understand exactly how fluids transfer heat, and you'll master the language engineers speak: Reynolds, Prandtl, Nusselt, Grashof, and Rayleigh numbers. Let's begin. First, let's understand what convection actually is. Imagine you're holding a hot cup of coffee. The heat from that coffee moves to your hand. But how? That's where convection comes in. It's heat transfer through the movement of fluids, whether liquid or gas. Now, there are two types of convection, and understanding the difference is critical. Natural convection. Think about heating water in a pot. What happens? The water at the bottom gets hot first. Hot water becomes less dense, lighter, so it rises. Cool water at the top is more dense, heavier, so it sinks. This creates a circular motion, a loop. No pumps, no fans, no external force, just density differences caused by temperature differences. That's natural convection, nature doing its thing automatically. Real-world examples: hot air rising from a radiator, ocean currents driven by temperature differences, the breeze you feel near a campfire. Forced convection. Now, what if we don't want to wait for nature? What if we want to force the fluid to move faster? That's forced convection. We use mechanical means, pumps for liquids, fans for gases, to agitate the fluid artificially. This promotes much better mixing and faster heat transfer. Real-world examples: your car's radiator with a water pump and cooling fan, air conditioning systems with blowers, industrial heat exchangers with pumps, your computer's cooling fan. The key difference: natural convection is passive and happens automatically. Forced convection is active and requires external energy. Now here's where engineering gets beautiful. How do we predict whether a flow will be smooth or chaotic? How do we know if heat transfer will be efficient or not? How do we design systems that work before we build them? The answer is dimensionless numbers. These are special ratios, numbers without units, that tell us everything about how a fluid will behave. They're like the fingerprints of fluid flow. Think of them as universal codes. A Reynolds number of 10,000 means the same thing whether you're working in meters or feet, with water or oil, in India or America. That's the power of dimensionless numbers. Let's master each one, step by step. First up, the Reynolds number, symbol Re. This is arguably the most important dimensionless number in fluid mechanics, named after Osborne Reynolds, who discovered it in 1883. What does it tell us? Reynolds number quantifies the battle between two forces in a flowing fluid: inertial force, the force of the fluid that results from its motion, think momentum, the fluid wants to keep moving. Viscous force, the force of friction within the fluid. Think of it as the fluid's internal resistance, its stickiness. This tries to slow the flow down. Reynolds number equals inertial force divided by viscous force. The formula: Re equals rho times V times L divided by mu. Or equivalently, Re equals V times L divided by nu, where rho equals fluid density, V equals velocity of flow, L equals characteristic length, like pipe diameter, mu equals dynamic viscosity, nu equals kinematic viscosity, which is mu divided by rho. Physical meaning: when Re is high, inertial forces dominate, flow is energetic and chaotic, turbulent flow. When Re is low, viscous forces dominate, flow is smooth and orderly, laminar flow. The critical values, memorize these. For flow inside circular pipes, Re less than 2,300, laminar flow, smooth, predictable, layers slide over each other. 2,300 less than Re less than 4,000, transition zone, unstable, unpredictable. Re greater than 4,000, turbulent flow, chaotic, mixing, swirling eddies. Most industrial piping systems operate in the turbulent regime because turbulent flow provides better heat transfer and mixing. Critical Reynolds number. This is the RE value where flow transitions from laminar to turbulent. For circular pipes, it's approximately 2300. But remember, this value changes for different geometries. A flat plate has a different critical RE than a pipe. Quick check. Notice RE has no units. Density times velocity times length divided by viscosity, all units cancel out. That's what makes it dimensionless and universal. Next, the Prandtl number, symbol PR, named after Ludwig Prandtl, the father of modern aerodynamics. What does it tell us? Prandtl number compares two molecular transport properties: momentum diffusivity, how fast momentum spreads through the fluid, that's kinematic viscosity, nu. Thermal diffusivity, how fast heat spreads through the fluid, that's alpha. PR equals nu over alpha equals momentum diffusivity divided by thermal diffusivity. Or using other properties, Prandtl equals mu times Cp divided by K, where mu equals dynamic viscosity, Cp equals specific heat capacity, K equals thermal conductivity. Physical meaning. Prandtl tells us, does momentum spread faster than heat, or does heat spread faster than momentum? When Prandtl is less than 1, heat diffuses faster than momentum. Example, liquid metals, Prandtl approximately 0.01. Excellent heat conductors. Thermal boundary layer is thicker than velocity boundary layer. When Prandtl equals approximately 1, heat and momentum diffuse at similar rates. Example, gases like air, Prandtl approximately 0.7. Balanced behavior. When Prandtl is greater than 1, momentum diffuses faster than heat. Example, water, Prandtl approximately 7. Oils, Prandtl approximately 100 to 1000. Velocity boundary layer is thicker than thermal boundary layer. Why does this matter? Prandtl number appears in every convection heat transfer correlation. It's essential for calculating heat transfer coefficients in forced convection. Verification, check that it's dimensionless, nu meters per second squared, divided by alpha meters per second squared, units cancel out. Now for something powerful, the Nusselt number, symbol Nu, named after Wilhelm Nusselt, pioneer of heat transfer theory. What does it tell us? This is the number for convection heat transfer. It answers the question, how much better is convection at transferring heat than compared to pure conduction through the same fluid layer? Nu equals the convective heat transfer divided by the conductive heat transfer. The formula, Nu equals H times L divided by K, where H is the convective heat transfer coefficient, W per meter squared K, L is the characteristic length, K is the thermal conductivity of the fluid. Physical interpretation, Nu equals 1, convection provides no enhancement, only conduction is happening. Nu equals 10, convection is transferring heat 10 times more effectively than pure conduction. Nu equals 100, convection is 100 times better than conduction. In most industrial applications, Nu ranges from 2 to several thousand. Why is this so important? Because we want to find H, the heat transfer coefficient, to design heat exchangers, cooling systems, everything. Nusselt number correlations, based on experiments, let us calculate Nu, and from Nu, we can find H. Example correlation, Nu equals 0.023 times Re raised to the 0.8 times Prandtl raised to the 0.3 for turbulent pipe flow. Quick check, dimensionless, H watts per meter squared K times L meters divided by K watts per meter K, units cancel out. Moving to natural convection, the Grashof number, symbol GR. This is the Reynolds number's cousin for natural convection flows. What does it tell us? Grashof number quantifies the ratio of buoyancy force divided by viscous force. In natural convection, flow is driven by buoyancy, hot fluid rises, cold fluid sinks. Grashof tells us how strong this buoyancy-driven flow is. The formulas? The general form is GR equals G times beta times delta T times L cubed divided by nu squared, where G equals gravitational acceleration, 9.81 meters per second squared, Beta equals thermal expansion coefficient, 1 over K. Delta T equals temperature difference, L equals characteristic length, nu equals kinematic viscosity. But the formula changes based on geometry. For vertical flat plates, GR equals G times beta times Ts minus T infinity times L cubed divided by nu squared. For pipes and bluff bodies, GR equals G times beta times Ts minus T infinity times D cubed divided by nu squared, where D equals the diameter for pipes or cylinders. Physical meaning: high GR, strong buoyancy forces, vigorous natural convection, more heat transfer. Low GR, weak buoyancy forces, weak natural convection, less heat transfer. Similar to Reynolds number, GR less than 10 to the 9th, laminar natural convection, GR greater than 10 to the 9th, turbulent natural convection. In between, transition zone.
Dimensionless check. Meters per second squared times 1 over K times meters cubed over meters squared per second squared. All units cancel. Finally, the Rayleigh number, symbol Ra. This is the ultimate dimensionless number for natural convection. What is it? Rayleigh number is simply the product of Grashof and Prandtl numbers. Ra equals Gr times Pr. The formula: Ra equals G times beta times delta T times L cubed over nu times alpha. Or Ra equals G times beta times delta T times L cubed times Pr over nu squared. What does it tell us? Rayleigh number combines everything that matters in natural convection: buoyancy effects from Grashof, fluid properties from Prandtl, geometry, characteristic length, temperature difference. It tells us, will natural convection be strong enough to matter? Critical values: Rayleigh number less than 10 to the 8th, laminar natural convection. Rayleigh number greater than 10 to the 9th, turbulent natural convection. In between, transition zone. Applications: designing passive cooling systems, no fans needed, building insulation and ventilation, electronic device cooling without active cooling, atmospheric and oceanic flows, solar collectors. The big picture: for forced convection, use Reynolds number. For natural convection, use Rayleigh number. When Ra is very high, natural convection is strong and might be all you need. When Ra is low, you might need forced convection, fans or pumps. Dimensionless verification: Grashof dimensionless times Prandtl dimensionless equals Ra dimensionless. Let's step back and see the complete picture. The hierarchy: convection type 1, forced convection, flow driven by pumps or fans. Key number, Reynolds number, Re, tells us laminar or turbulent. Also need Prandtl number, Pr, tells us fluid properties. Calculate Nusselt number, tells us heat transfer coefficient. Typical correlation: Nusselt equals F of Rayleigh, Prandtl. Convection type 2, natural convection, flow driven by buoyancy. Key numbers, Grashof and Rayleigh number, tell us how strong is buoyancy. Also need Prandtl number, Pr. Calculate Nusselt number, again to find heat transfer coefficient. Typical correlation: Nusselt equals F of Rayleigh or F of Gr, Pr. Real-world design process: identify natural or forced convection. Calculate relevant dimensionless numbers. Check laminar or turbulent. Use appropriate correlation to find nu. Extract H, heat transfer coefficient. Design your system. Example scenario: you're designing a radiator. Calculate Reynolds number. Check if flow is turbulent, usually yes. No Prandtl number for your coolant. Use turbulent flow correlation. Nusselt equals 0.023 Rayleigh to the 0.8, Prandtl to the 0.3. Calculate Nusselt, then find H. Now you can size your radiator. And there you have it. From the basics of natural and forced convection to mastering 5 critical dimensionless numbers. Reynolds number, the gatekeeper between laminar and turbulent flow. Prandtl number, the fluid property fingerprint. Nusselt number, the convection enhancement factor. Grashof number, the buoyancy force indicator. Rayleigh number, the natural convection master parameter. These aren't just formulas to memorize, they're the language of thermal engineering. Every heat exchanger, every cooling system, every HVAC design uses these numbers. Master them, and you master heat transfer. Now, I know what you're thinking. This is great theory, but can I actually apply this? Well, don't go anywhere, because we're about to do exactly that. Coming up next in this same video, we've prepared complete worked examples, Real engineering problems that will take everything you just learned and put it into action. We'll calculate Reynolds number for pipe flows, determine if convection is laminar or turbulent, find heat transfer coefficients using Nusselt correlations, and solve actual thermal systems step by step. These aren't textbook problems. These are the exact type of calculations engineers do in industry every single day. The theory you just learned is powerful, but these 5 examples, they'll transform you from someone who understands the concepts to someone who can solve real problems. So stick with me, because the next part is where everything clicks into place and you truly master convection and dimensionless numbers. Until then, keep learning, keep engineering, keep pushing boundaries. This is Academic Engineering signing off.
Now we'll explore the physical mechanism of convection and dimensionless numbers through practical examples. Let's start with example 1. A long 10-centimeter diameter pipe whose external surface temperature is 110 degrees Celsius passes through some open area that is not protected against the winds. We need to determine the rate of heat loss from the pipe per unit length when the air is at 1 atmosphere pressure and 10 degrees Celsius, and the wind is blowing across the pipe at a velocity of 8 meters per second. Now that we understand the problem, let's organize our solution systematically. I'm setting up 3 boxes: properties, given data, and calculated values, to keep our work organized and clear. Let's extract the given data from the problem. The diameter of the pipe is 0.1 meters, or 10 centimeters. The surface temperature, Ts, is 110 degrees Celsius. The ambient air temperature, T infinity, is 10 degrees Celsius. The film temperature is the average, that's 60 degrees Celsius. The pressure is 1 atmosphere. The wind velocity is 8 meters per second. The perimeter per unit length is pi times d, which equals 0.31416 meters. And the surface area per unit length is 0.31416 square meters. Now, let's look up the properties of air at 1 atmosphere and 60 degrees Celsius. The density, rho, is 1.059 kilograms per cubic meter. The specific heat, Cp, is 1.007 kilojoules per kilogram Kelvin. The kinematic viscosity, nu, is 1.896 times 10 to the minus 5 square meters per second. The thermal conductivity, K, is 0.02808 watts per meter Kelvin. The coefficient of thermal expansion, beta, is 3.002 times 10 to the minus 3 per Kelvin. And the Prandtl number is 0.7202. Excellent. We have all the data and properties we need. Let's solve this step by step. Step 1. First, we calculate the Reynolds number to determine the flow regime. Reynolds number equals velocity times diameter divided by kinematic viscosity. Substituting the values, 8 times 0.1 divided by 1.896 times 10 to the minus 5. This gives us Reynolds number equals 42,194.1. Since this is greater than 4,000, we have turbulent flow. Step 2. Now we calculate the Nusselt number. For turbulent flow over a cylinder, we use the Churchill-Bernstein correlation. This is a complex formula involving Reynolds and Prandtl numbers. After careful calculation, we get nu equals 124.453. Step 3. Let's find the heat transfer coefficient, H. From the definition of Nusselt number, H equals K times nu divided by D. Substituting, H equals 0.02808 times 124.453 divided by 0.1. This gives us H equals 34.95 watts per square meter Kelvin. Step 4. Finally, let's calculate the heat transfer rate per unit length. Using Newton's law of cooling, Q dot equals H times AS times the temperature difference. Substituting, Q dot equals 34.95 times 0.31416 times bracket 110 minus 10 close bracket. That's times 100 degrees. This equals 1,098 watts. or 1.098 kilowatts per meter length of pipe. And there's our answer. The convective heat loss from the pipe is 1.098 kilowatts per meter. This means for every meter of pipe exposed to the wind, the pipe loses about 1.1 kilowatts of thermal energy to the surrounding air through forced convection. Excellent work. Now, let's move on to example 2, where we'll apply these concepts to a different scenario.
All right, class, now we move on to example 2. This time, we'll look at natural convection, which is different from the forced convection we just studied. Listen carefully to the problem. A 6-meter-long section of an 8-centimeter diameter horizontal hot water pipe passes through a large room whose temperature is 20 degrees Celsius. If the outer surface temperature of the pipe is 70 degrees Celsius, we need to determine the rate of heat loss from the pipe by natural convection. Notice the important note here. We must use the appropriate equation to calculate the Nusselt number. Keep this in mind. Good. Now that everyone understands what we're looking for, let's set up our solution. As before, I'm organizing everything into 3 sections: properties, data, and calculated values. This keeps our work neat and easy to follow. Let me extract all the given information from the problem. Pay attention to each value. The length of the pipe, L, is 6 meters. The diameter is 8 centimeters, which equals 0.08 meters. Always convert to SI units. The surface temperature, TS, is 70 degrees Celsius. The room temperature, T infinity, is 20 degrees Celsius. The film temperature for properties, that's the average, 45 degrees Celsius. The surface area is pi times d times L, which gives us 1.508 square meters. Now, let's look up the air properties at 1 atmosphere and 45 degrees Celsius. Everyone following along? Density, rho, is 1.109 kilograms per cubic meter. Specific heat, Cp, is 1.007 kilojoules per kilogram Kelvin. Kinematic viscosity, nu, is 1.750 times 10 to the minus 5 square meters per second. Thermal conductivity, K, is 0.0299 watts per meter Kelvin. The thermal expansion coefficient, beta, this is important for natural convection, is 3.145 times 10 to the minus 3 per Kelvin. And the Prandtl number is 0.7241. Perfect. Everyone has all the data? Good. Now, here's where natural convection gets interesting. Let's solve this step by step. Step 1. For natural convection, we first need the Grashof number. This is new compared to forced convection. Grashof number equals G times beta times the temperature difference times d cubed, divided by nu squared. Substituting carefully, 9.81 times 3.145 times 10 to the minus 3 times 50, that's our temperature difference, times 0.08 cubed divided by 1.750 times 10 to the minus 5, all squared. This gives us Grashof number equals 2,581,135.2. Step 2. Now we calculate the Rayleigh number. Rayleigh number is simply Grashof number times Prandtl number. Easy, right? So, 2,581,135.2 times 0.7241 equals 1,869,000, or 1.869 times 10 to the power 6. Write this down. Step 3. Time to find the Nusselt number. This is the tricky part, so pay close attention. For natural convection over a horizontal cylinder, we use a special correlation formula. This is the Churchill-Chew correlation. It looks complex, but we just need to plug in our Rayleigh number and Prandtl number carefully. After careful calculation, we get Nusselt equals 17.4, much smaller than forced convection. Notice that? Step 4. Let's find the heat transfer coefficient, H. Almost there, class. Using Newton's law of cooling, H equals K times Nusselt divided by D. Substituting 0.0299 times 17.4 divided by 0.08, we get H equals 5.87 watts per square meter Kelvin.
Notice this is much lower than forced convection because natural convection is weaker. Step 5. Finally, the heat transfer rate. Almost there, class. Using Newton's law of cooling, Q dot equals H times AS times the temperature difference. Substituting 5.87 times 1.508 times bracket 70 minus 20, close bracket. That's 5.87 times 1.508 times 50 degrees, and we get 442.6 watts. Excellent work, everyone. Here's our final answer. The heat loss by natural convection is 442.6 watts. Compare this to example 1. Forced convection gave us over 1,000 watts, but natural convection only gives us about 443 watts. This shows that forced convection is much more effective at heat transfer than natural convection. Great job following along. Now, let's move on to question 3, where we'll explore another interesting scenario.
Now let's start example 3. This is going to be interesting. We'll solve the same problem for 3 different orientations. Listen carefully. Consider a 0.6 by 0.6 meter thin square plate in a room at 30 degrees Celsius. One side of the plate is maintained at 90 degrees Celsius while the other side is insulated. We need to determine the rate of heat transfer from the plate by natural convection for the following cases. Case A, if the plate is vertical. Case B, if the plate is horizontal with hot surface facing up. And case C, if the plate is horizontal with hot surface facing down. Important note here, we must use the appropriate equation for each case. The orientation matters a lot in natural convection. Got it? Same plate, same temperatures, but different orientations give us different heat transfer rates. Setting up our workspace, properties, data, and calculated values, this time we'll track all 3 cases. Let me write down the common data that applies to all 3 cases. The side length L is 0.6 meters. Surface temperature is 90 degrees Celsius. Ambient temperature is 30 degrees Celsius. Film temperature, 60 degrees Celsius. Surface area is L squared, which equals 0.36 square meters. Air properties at 1 atmosphere and 60 degrees Celsius. You should be getting familiar with these by now. Kinematic viscosity, nu, is 1.896 times 10 to the minus 5 square meters per second. Thermal conductivity, K, is 0.02808 watts per meter Kelvin. Thermal expansion coefficient, beta, is 3.003 times 10 to the minus 3 per Kelvin. And Prandtl number is 0.7202. All right, class, let's solve all 3 cases systematically. Ready? Starting with case A, the vertical plate. This is the simplest orientation. Marking case A in our calculated values box. Step 1, Grashof number. Grashof equals G times beta times temperature difference times L cubed divided by nu squared. This gives us 1.063 times 10 to the 9th. That's a large number. Step 2, Rayleigh number. Rayleigh equals Grashof times Prandtl. We get 7.656 times 10 to the 8th. Step 3, Nusselt number for a vertical plate. We use the Churchill-Chew correlation for vertical surfaces. This gives us nu equals 113.4. Step 4, heat transfer coefficient. H equals K times nu divided by L. We get H equals 5.306 watts per square meter Kelvin. Step 5, finally the heat transfer rate for the vertical orientation. Q dot equals H times AS times delta T. We get 115 watts for the vertical plate. There we have it. Answer for case A. For the vertical plate, the heat transfer rate is 115 watts. Good. Now let's see what happens when we make the plate horizontal with the hot surface facing up. Moving on to case B. Case B, horizontal plate with the hot surface facing up. The physics changes here. Marking case B in our box. Important. For horizontal plates, we need a different characteristic length. LC equals area divided by perimeter, which equals L over 4, giving us 0.15 meters. Notice it's smaller. Now calculating Grashof and Rayleigh with this new characteristic length. Grashof equals 1.66 times 10 to the 7th, much smaller than case A. Rayleigh equals 1.196 times 10 to the 7th. Nusselt number for hot surface facing up. We use a different formula. Nu equals 0.1 times Rayleigh to the 1/3 power, which gives us 22.86, much lower than case A. Now finding H and the heat transfer rate. H equals 4.2 watts per square meter Kelvin, and Q dot equals 92.43 watts. Notice this is less than the vertical case. Answer for case B. Hot surface facing up, 92.43 watts. Lower than vertical because convection is less effective in this orientation. Now, for the last case, what happens when the hot surface faces down? Let's find out. Final case, everyone. Stay focused. Case C, horizontal plate with the hot surface facing down. This should give us the lowest heat transfer. Marking case C. Using the same LC equals 0.15 meters. Rayleigh number is the same, 1.196 times 10 to the 7th, but now we use a different formula for hot surface down. Nu equals 0.27 times Rayleigh to the 1/4 power, giving us 15.878, even lower. Final calculation, H and Q dot. H equals 2.9724 watts per square meter Kelvin, the lowest of all three cases, and Q dot equals 64.2 watts. This is the minimum heat transfer rate. And there's our final answer. Hot surface down, 64.2 watts, the lowest of all three orientations. Excellent work, everyone. Let me summarize. Vertical plate gave us 115 watts, hot surface up gave 92.43, and hot surface down gave only 64.2. This shows that orientation really matters in natural convection. The vertical orientation is most effective, while hot surface down is least effective because the hot air is trapped underneath. Great job following through all three cases. Now let's move on to example 4.
All right, class, let's start problem 4. This is a real-world application, an airplane wing. Pay close attention to this problem statement. It's a practical engineering scenario. An airplane flies with a speed of 450 kilometers per hour at an altitude of 8,000 meters, where the surrounding air has a temperature of 1 degree Celsius. The airplane wing, idealized as a flat plate 6 meters long and 1.2 meters wide, is maintained at 19 degrees Celsius. If the flow is made parallel to the 1.2 meter width, we need to calculate the heat loss from the wing. This is important for aircraft design. Got the picture? High altitude, cold air, and a heated wing. Let's analyze this. Setting up our organized workspace. Properties, given data, and calculated values. You know the drill by now. Let me extract all the important data. Watch carefully as I convert units. Velocity is 450 kilometers per hour. Converting to meters per second, that's 125 meters per second. Always work in SI units. Air temperature, T infinity, is 1 degree Celsius. That's cold. Wing surface temperature, TS, is 19 degrees Celsius. The average temperature for properties, 10 degrees Celsius. We're at 8,000 meters altitude. This affects air properties. The characteristic length, LC, is 1.2 meters, the width, because flow is parallel to it. Surface area, both sides of the wing, so 2 times 6 times 1.2, which equals 14.4 square meters. Now, air properties at 10 degrees Celsius. Notice we're using the average temperature. Kinematic viscosity, nu, is 14 times 10 to the minus 6 square meters per second. Thermal conductivity, K, is 0.024 watts per meter Kelvin. And the Prandtl number is 0.73. Perfect. Everyone has all the data? Good. Now let's solve this aviation problem step by step. Step 1. Calculate the Reynolds number. This tells us what type of flow we have. Reynolds number equals velocity times characteristic length divided by kinematic viscosity. Substituting, 125 times 1.2 divided by 14 times 10 to the minus 6. This gives us Reynolds number equals 10.7143 times 10 to the power 6. That's over 10 million. Since Reynolds number is much greater than 5 times 10 to the 5, we definitely have turbulent flow and forced convection on a flat plate. Step 2, Nusselt number. This is where we apply the turbulent flow correlation. For turbulent flow on a flat plate, we use this specific correlation. Nusselt equals 0.037 times Reynolds number to the power 0.8 times Prandtl number to the power 1/3. Substituting our values, 0.037 times bracket 10.7143 times 10 to the 6 close bracket to the power 0.8 times bracket 0.73 close bracket to the power 1/3. After careful calculation, Nusselt equals 14,015.6304. That's a large Nusselt number due to turbulent flow. Step 3. Finding the heat transfer coefficient, H. Stay with me, we're almost there. From the Nusselt number definition, Nusselt equals HLC over K. Rearranging, H equals Nusselt times K divided by LC. Substituting, H equals 14,015.6304 times 0.024 divided by 1.2. We get H equals 280.313 watts per square meter Kelvin. Notice how high this is. Turbulent flow is very effective. Step 4, finally, the heat loss from the wing, our main objective. Using Newton's law of cooling, Q dot equals H times AS times the temperature difference between surface and air. Substituting, Q dot equals 280.313 times 14.4 times bracket 19 minus 1. That's 280.313 times 14.4 times 18 degrees. This equals 72,659.13 watts, or converting to kilowatts, 72.659 kilowatts. Excellent work, everyone. Here's our final answer. The heat loss from the airplane wing is 72.659 kilowatts. Think about this. The wing is losing almost 73 kilowatts of heat to the cold surrounding air at high altitude. This is why aircraft heating systems are so important. The high velocity creates turbulent flow, which increases heat transfer significantly. Outstanding! You've successfully analyzed heat transfer on an airplane wing. This is real aerospace engineering.
And that's a wrap. You've not only learned the theory behind convection in dimensionless numbers, but you've also solved 4 real engineering problems from scratch to mastery. Like this video if you can now confidently calculate Reynolds, Prandtl, Nusselt, Grashof, and Rayleigh numbers. Subscribe to Academic Engineering for more expert-level engineering content explained simply, from fundamentals to professional applications. Comment below which of the 5 examples helped you the most, or share your own convection problem you'd like us to solve. You've mastered the basics, now let's take it to the next level. See you in the next one.